Okay, so the first thing I want you to do is to clone this repository from FPGA now and check out the dev branch. So I've already done this and I'm going to go straight into Vivado. So next, launch Vivado 2024.1 and go into the directory where you have cloned this source code. So for me, that's going to be this directory. Work, FPGA now, market data POC. Notice how the slashes cannot be backslashes. They have to be reversed from what Windows gives you. Now in this repository, let me go back to GitHub. We have a directory called Vivado, KR260, POC KR260. So we're going to go into here. Also, please note for the KR260, you have to manually set the board into boot to JTAG mode every time you power on the board. There is a tickle script that you can use to do this faster, but that's one of the issues with the KR260 because the code will work, but once you start using hardware on the device, it'll fail and you won't know why and you'll forget. So anyway, we're going to go into Vivado, and it's quite good with its autocomplete. Look, I could do autocomplete. And again, so now I'm in this directory. I can type pwd, I can type dir, can't type, oh, it supports ls as well. So now I'm going to type source./poc, and this is going to generate a very basic design. It doesn't have the 10 gigabit components, the Ethernet subsystem, or anything else. But what I want to note is that to make it easier to export your design, this project will be created in a new directory. It's going to be called, I believe, POC KR260. But it references the constraints file in an outside directory, and it references the block design, the BD file, and the wrapper, which are in different directories. So that way, we make changes, we just commit these files in these directories, not the ones in the large one, which takes up a lot of space. So again, we could see constraints file. It's pretty basic here, vanilla. I just enable the fan and Bitstream compression and the design wrapper, which is automatically managed by Xilinx. So what I'm going to do is I'm going to click on Open Block Design. And then I'm going to expand this window to full size. So for everything to work, there's a bunch of settings you have to set in the Zinc. Now, I already did this for this design, but I'm going to double click on it. So go through the wizard so you can see them for yourself. So the first thing is we need USB 1, and that is to communicate, UART 1, so that we can communicate to the console over the application. So if you just click on that, you'll see the MIO pins, and these are pretty much defaults. The next thing is we're going to go into the PSPL configuration and configure our interfaces. So the first one we want is HPM0 full power domain. And you don't necessarily have to pick 128-bit, but I just chose that. And then we need another one for the slave interface. So the slave interface is going to be under here, HPC0 FPD for full power domain, speed 128. The next thing we need is the interrupts. So under general, interrupts, PL to PS, which is, programmable layer to processing system. Just a simple one will enable it. Okay, so that's all fine. Now we're going to go to clock configuration. We want to see the output clocks, and we're going to go on low power domain clocks and the PL fabric clocks. So as you can see, we have PL0 set to 100 megahertz, not using PL1, but that's okay for now. And the type is IOPLL. Okay. And then finally, we go back to the block design. And in my notes, I see that I've enabled USB 1. I forget what I used this for. We'll get to that later. So anyway, I'm going to click OK. And we're going to start off. First, you see how this is the fan It's connected to this TTC 0 wave IP. We're going to create a GPIO to control the SFP LED. So we're going to click Add IP. I'm going to type GPIO. And we're going to configure it to have custom, one channel, all outputs, and we want the width to be 2. All right, then we're going to make this external. We're going to right-click Properties, and we're going to rename it SFP LED. Hold on. All right. Next, we're going to add IIC, or I2 squared, for controlling the SFP, or communicating with the SFP. So we're going to do IIC. There's only one IP here. We're going to double click on this. We're going to make sure these settings, I believe, are the default. So it's 100 kilohertz, 7-bit address mode, inertial delay 0, active state of SDA1, GPIO output with 1, default GPIO port output value 0. This is automatic, so no need to worry about that. Now we're going to make this, again, we're going to right click, we're going to see make external. We're going to rename this port. We're just going to call it SFP IIC. Enter. Now, what's next? So this board has an SFP transmit disable. As long as that is driven high, the SFP port is going to be disabled. So we're going to set up a constant to drive the value to low, so that way it will not be disabled. So we're going to right click and do make external. Oh, first of all, we're going to click, we're going to change the width, it stays at 1, but the value becomes 0. Click OK. Now we're going to right click, we're going to see make external. We're going to go here and we're going to rename it to SFP TX BIS. All right, so now I'm going to have to pause the video here because I want to make sure we're not using the Smart Connect. I'm not exactly sure what happens if I just tell it to do connection automation. Let's click on it anyway to see. It says, yeah, I may have to add an AXI interconnect and then tell it to connect to the AXI interconnect because I don't want it to use Smart Connect. Okay, we're back. So let's clean this up. All right, so now if I click Run Connection Automation, it's going to create a new AXI interconnect. Everything looks fine because you can see that the AXI interconnect it's the old style one, because the reason we want this is because we're going to create a DMA controller and I want to set custom clock for the receive and transmit channels. I want those to be running at 156.25 megahertz to match the SFP clock. All right, so now we're going to add the AXI Ethernet subsystem. So we type AXI Ethernet, and we're going to pick, where's the 10 gigabit one? We're looking for the 10 gigabit. There it is. Okay, so it's 10 gigabit, 25 gigabit Ethernet subsystem. We double click. All right. So first thing we do, we double click on it. Oh, my window's a little too small. Let me shrink it down. All right, first thing we're going to do, not Mac. We want this, PCS PMA. Can't really change anything else. Don't worry about the number of cores, but we do care about this. We want to change it to base R. We can leave this as its default. Over here in the Mac options, And we're not going to deal with the timestamping logic right now. GT selection. If you look in here, you'll see that there's only one option because it picks. I don't fully understand what this does, but that's okay for now. We're not going to do anything here. We're just going to click OK. All right, so now if we click connection automation, it should connect. Let's see. Let's see what it says. The D clock. Okay, the D clock. Well, this should be made external. This should be made external. So this is the gigabit transceiver reference clock, which we have to configure to the board, to the appropriate pin. The gigabit transceiver serial port. So this has both the RX and TX for the gigabit transceiver, which again we have to configure using constraints. It should be made external. RX core clock. Now this should loop back and map into the RX core clock. It should map to RX clock out. So I'm going to leave this out for now. Now this AXI interface should connect to the AXI interconnect that we see over there. So I'm just going to configure these right now. And let's see where the AXI connection goes. And there it is, AXI interconnect. Looks good. Now I'm looking at my notes, and the D clock and the AXI clock, D clock should map to that. Let's see what the connection automation says. It's saying clock source will be PL clock 0. So let's see if this clock is connected to PL clock 0. Yes, it is. So I'm going to click Run Connection Automation and hook that up. Now what about RX core clock 0? Okay, this makes sense because look, it's the clock recovered from the SFP, and it will go back and loop around. You'll see in a second. Hold on. Click OK. So look, RX core clock 0 is connected to RX clock out 1. We're also going to use this clock to power our FIFOs, our receive and transmit FIFOs. All right, so let's a little cleanup. So let's see, what else can we do here? GTRTL, let's rename this. Let's call it, I think GTRTL is fine. How about RX ref clock 1? Let's see what it's called. Let's rename this. Let's call it GT ref CLK. All right, so now let's go back to this core. Let's move it over so we have some space to look to breathe. So now what we want to do is we have to configure a bunch of these inputs. So let's start with the clock out selection. So we're going to make a constant. The width is going to be 3, and the value is going to be 5. You have to think of it in terms of binary, and that's going to select the appropriate clocks for the output RX and TX. All right, so let's just wire these up. Now the next thing we're going to configure is the GT-Wiz reset TX data path. This should come from PL reset 0. So we're going to take this and we're going to connect it to GT-Wiz RX and TX data path. Now the PL clock is active low, active high, but this one doesn't mention if it's active high or active low. But regardless, we're going to flip it. So we're going to say logic I'm gonna make it width 1, not. I'm gonna plug it into both. And we're gonna go where I said the PL reset. Actually, there it is, the N. I thought the N means it's active low, but here it's not with an N, so it's active high. All right, so we got that. Next, we have system reset. We have declock. Now we have this. Now, what about RX reset 0 and TX reset 0? So these are going to come from the DMA. We haven't set up the DMA yet, so I have to skip it for now. So the RX reset and TX reset are going to be set by the DMA. MII TX, MII RX, we're going to use some special IP from the NetFPGA board to convert the signals into AXI, so we can use it on in our what do you call it, the SDK Vitis. All right, so now what we're going to do is we're going to add a DMA controller. So we go add, just type DMA. That's it, simple. Now we double click. We're going to get rid of the status stream, we don't care. We're going to set stream data width to 64, and it sets the data width. Same thing over here. Set it to 64, sets it automatically over there. Unaligned transfers doesn't really matter. I guess, you know, let's enable it. Let me shrink this window a little bit so you can see the whole thing. I'm going to click OK. So now here's what happens. One is for controlling the actual DMA device, and this is stream to memory mapped. And then here is the master, memory mapped to stream. And then these are for controlling. This is a scatter gather channel, and this is for controlling memory map to stream, which corresponds to this one. Stream to memory map corresponds to that one. So if we do run connection automation, it should connect S AXI light to my AXI interconnect. So let's see what it says. Okay, it's going to go to FP full power domain HPM 0. That looks good. And one for the slave as well. Actually, this is for the auxiliary interconnects. So let's see what happens. So let's follow AXI light. Zoom out. There it is. It goes to the AXI interconnect, which goes to the HPM0 FPD. Let's follow this one, MM2S. This, oh, smart connect. That's going to be a problem. All right, what I could do is I can delete this smart connect. Let's just follow it completely. Yeah. All right, so we're going to delete this smart connect. We're going to add another AXI interconnect. And what we're going to do is we're going to run connection on background task. Wait. Run connection automation. Let's see where it says it's going to connect. It's going to connect it to the PL clock. All right. All right, so let's follow this. There it is. Looks good. And this master interface, where's it going? It's just going, okay, there we go. So now we don't need this extra master connection, so I'm just going to configure and say one master interface. So now you see the run connection automation is still there. It's for the other two auxiliary ports. They have to go to the same AXI interconnect. So let's see. We have 1, 2, 3. They all go to the same AXI interconnect. So now we have to add some FIFOs. So we're going to add AXI 4 stream data FIFO. This one right here. Something's happening in the background. Oh no, it's my other Vivado. All right, so packet mode, yes. I think that'll happen automatically. So let me just click. I'm using tkeep, so I might as well enable it. So let's see if this will connect, or actually I think I have to connect it myself. So I'm going to rename this to TX data FIFO. So memory mapped to stream means what's in memory is going to be streamed to the transmit FIFO, and that's going to go out of the SFP. So I connect that. The other side is going to go to the XGMII, the NetFPGA IP that I'm going to show where you can download from in a bit. So we have the TX FIFO. Now we're going to make another one. We're going to call it RX FIFO. So you type XC4, what is it? Data FIFO. Axi4 stream data FIFO. You know what? Let's take a look. Let's see if the data was updated to 64-bit. It still says 1 byte. Let's check the pins. Yeah, too small. Okay. So I'm going to double click. I'm going to manually set this to 8 bytes because we want 64-bit. It'll automatically be updated in here. Yep, there it is, 63. We're going to do the same thing for this one. 8. We're going to enable packet mode. We're going to enable tkeep. And that should be it. And now here we're going to connect the master to the transmit. All right. So now what's important here is that we now have these reset pins. So we could take the first one, which is memory mapped to stream. What's memory mapped to stream? It's this one right here, which is our transmit FIFO. So we're going to take memory mapped to stream, plug it into TX reset. So we're going to go back to the Ethernet IP. Here's TX reset, it's empty. We're going to take a reset logic, utility vector logic reset. I'm going to paste it, and I'm going to rename it. I'm going to call this TX reset. Let's double check just to make sure it's correct. Okay, not size length 1. So this is going to go to TX reset. We're going to take another one. And we're going to call this one RX reset. Got to get rid of that one. So RX reset. So what did we say is the TX? It's the top one, which is MM2X, S, memory mapped to stream. So let me just double check that everything's correct. Yes, it is. So I'm going to take MM2S, scroll to the right to TX. Then I'm going to do the RX. Hold on, I want to double connect. Okay, there we go. And this is going to go to the stream to memory mapped. And that's it. All right, so we have 2 interrupt pins. So we're going to add a concat. Width of 2 is fine for now. So we're going to take the interrupt from the transmit FIFO and the receive FIFO, plug it in, hook it up. Okay, I'm looking at my design, and I want to plug in the interrupt for the IC. And that's it. The rest is just extra that I have. All right, so I'm going to make one more pin. I'm going to take one more pin, go all the way to the right where the I2C interface interrupt, and we're configured. All right, so I'm going to take a break right now so I can find the source code for this to show you. Okay, so what we're going to do now is we're going to download some IP to convert the MII signals coming from the AXI Ethernet subsystem into valid AXI streams that work with this XGStream data FIFO that goes into the DMA, which we can then access from the processing system. So after some Googling, I found it. It was under this guy's webpage. Let's see, Marco Forconesi. So the files that we need are access to GMII.v, the opposite direction, XGMII to AXI, and the includes file. Let's click on one of these. How about, all right, download raw file. Okay, let's do the other one. And the includes file. Oops. Let's just let's see if we can open one up. Yep, looks fine. There it is. All right, take these 3 files. I'm going to cut them. And now here's the project. Remember how I said before this directory will be created? Well, we don't want to put the source code in here. So what I'm going to do is I'm going to make a new directory. I'm going to call it my HDL. So I'm going to go into this directory. Just going to paste it. Now this is a small FPGA design. I'm not like adding a bunch of other Verilog VHDL files, so I don't really have to make subdirectories to be organized. So okay, those files are added. So now I'm going to go back to the Vivado design, go to the sources, and I'm going to say add. Add or create design sources. Go add files. Here, no, wrong project. We go back to the source code. So remember this new directory, my HDL. I'm going to add all 3 files. Verilog, reload, everything looks fine now. Okay, so here's one quick thing. XGMII to AXI. I'm sorry, wrong one. Access to XGMII. This is the read. I'm wrong again. I made a change to one of these files. I just have to figure out which one. Okay, I found it. So in XGMII to AXI, there's a reset and another reset, or an asynchronous active low reset. So what I wanted to do was get rid of this reset. So comment that out. Then save, and I'm going to get a couple of compilation errors. So let's see, right, line 150. Let's see. Right. Okay, this is the adapter part. I'm just going to use the same reset signal from above, and that should be fine. The reason I did this is because I don't want to have extra pins on the front panel, because it just makes things confusing and overloaded. All right, so back to here. Here's what we're going to do now. Which FIFO should we start with? We're going to start with the... I didn't rename this FIFO. Okay, this is the RX data FIFO. So we're going to write RX data FIFO. And the RX data FIFO goes to XGMII to AXI. So this is something I like about Vivado. It kind of reminds me of LabVIEW. You could just, can you? Drag something on there. I mean, not as easy to use as LabVIEW, but hey. So now, I'm going to take Let's see if I can plug it in directly. Oh, it takes it. All right. So the slave port goes to the interface. The configuration vector looks like it's going to be width 80, value 1. So I'm going to go constant. Now, these XGMII signals go to the AXI Ethernet subsystem on the RX pins. So we're looking at D right now. So D. We're going to take C. Plug that one in. Now the clock, let's see where the clock goes. The clock comes from the RX clock out. So I'm going to take this. I'm going to find the RX clock out. This looks like the one. Oops. And now reset. What about that one? The reset is inverted. So let's put a vector logic. Let's make it width of 1, not. And let's rename this. Let's call it RX RST N, because that's the output. And this reset comes from the SFP, the AXI Ethernet Subsystem, user RX reset. So there we go. Now what else do we have to do? We have to plug in these clocks. So let's go look at the RX data FIFO. The clock is the same as it is for the XGMII. And the reset is also the same as that which is going into the XGMII. So we're going to go clock, clock. We're going to go reset. Oops, do that. Reset, reset. So reset N, reset N, reset N. But this reset is sourced from the AXI Ethernet substream, but it's not N, so it's active high. So that's what we have for here. But now there's more to be done. These clocks. So let's see. Let's find the Ethernet DMA. So the clock for S2MM. How do we know it's S2MM? Click on this. Look, S2MM. So that's like an easy way to remember. So I'm going to go here. I'm going to right click. I'm going to say disconnect pin. I'm going to take that clock. Now I'm going to plug it into the same clock as this FIFO. There's more. We have to find now this clock on the AXI interconnect. So we take S2MM. So we click on S2MM. We find the AXI interconnect. And it's plugged into port 1. So we're going to go S port 1. We're going to take this S1. We're going to go back. We're going to find that FIFO. Make sure it's connected to the clock. So this is the clock for the FIFO and the XGMII. We're going to do the same thing for the reset. I'm not sure if I disconnected the reset, so I'm going to go back here. I did not. So click on the pin, say disconnect, then connect it. A reset pin. So now that means the clock for the FIFO, the XGMII, and the DMA that connects the DMA channel or port are all connected to the RX port of the Ethernet subsystem. Now we have to do the same exact thing, but for the transmit side. So let's see what's going on here now. Let me just check, make sure we got RX reset, we got RX clock. Now we need to do XGMII clock. This is the one. We'll start with this. So now we're going to go and we're going to find the other FIFO, the other direction. So this is the S2M. For now we want the MM2S. And let's see, here's the FIFO. So this clock, we'll go to the MM2S over here. So we're going to break one right there. Wait, did I do it clock to clock? All right, good. We're going to do the same thing with the reset. So we're going to copy this and paste it. But this time we're going to call it TX RST. And the clock source is going to be from the AXI Ethernet subsystem. So let's go follow all the way to the right. Where is it? TX reset. There we go. And where does the clock itself go? I'm sorry, where does the reset itself? It goes to the TX FIFO. Let's see, do we have the TX FIFO? There it is. Reset, reset. And it also goes to the AXI interconnect. So what are we dealing with? We're dealing with this one, MM2S. It goes to the FIFO. All right, what about the other one? This one, that goes to the AXI interconnect. It goes to port S0. So I'm going to take S0 and I'm going to cut both of these pins. And we're going to start with reset this time. So we're going to do reset. We're going to go down. We're going to go to the, well, I mean, I know it's this reset pin. And the clock goes to the next pin. So let's see if I can do this. Oops. Undo. I left it open so I know which port. That's it. So now we have to plug in IP on the other side. Now we have XGMII to access. Now we need to add access to XGMII. So I just drag it on. The clock and the reset are the same. And the configuration vector is also the same as before. So what I could do is, what that means is I could take this interface AXI, plug it in over there, hook up the clock, and hook up reset. Now, where's the configuration vector? Well, actually, it doesn't matter. I could just plug it in like that. Now, we're not reading good frames, bad frames, or any of these things. We're simply using the D and the C. So now let's go all the way to the right. Let's find the 64 pin. All right, now I think something is missing. Let's just see the clocks for the DMA. Let's save this design, see what happens. Let's see what it's complaining about. Run connection automation. AXI DMA 0. Oh, there we go. I think I know what's wrong. S is 0. These clocks are not driven. So let's start with, basically it said this clock is not driven. So let's see. It goes to, it's driving other devices. It's driving that device, but where is it coming from? Very good. All right, so let's find it. Let's see, access to GMII. Access to GMII is going to the TXMII clock. So where is it? TXMII clock. Now we need to do the same thing probably for the RX clock. Oh no, I think you got everything. So some design. Let's see how it looks. Okay, so XGMII to AXI. Let's follow it. The Ethernet subsystem receives an Ethernet frame. It sends it over the XGMII interface, data and control ports. It goes to this IP XGMII to AXI, which converts it or translates it into AXI. This FIFO then takes it, puts it into the DMA controller. This is the S2MM slot. So if we look at S2MM, we see that the clocks are all synchronized. And the clock is also on the AXI interconnect for channel 1. What's channel 1? S2MM. If we continue to follow this clock, we'll see that it comes from the RX clock of the AXI Ethernet subsystem, and it also loops back to power the RX core. We could do the opposite now for the TX. Let's see, where's the TX? All right, the TX comes in from access to XGMII. So where does it come from? It comes from the DMA channel MM2S. MM2S has the same clock. The clock comes from the TX clock on the Ethernet subsystem. And the MM2S signal goes to channel 0. Channel 0 has the same clock and the same reset. So data comes from the processing system to the DMA to this TX data FIFO, which then goes to the AXI to XGMII, which sends valid XGMII signals, which go into the AXI Ethernet subsystem. Okay, interesting. I think we got everything here. Let me just take a look at my reference design to make sure. I got TX disable, fan enable, SFP LED. I guess you don't really need that, right? SFP I2C. And then we got these serial port pins. Now we'll notice there are two RX, two TX, differential pairs. All right, now I'm not sure if you have to do this every single time, but we'll do it anyway. Generate output products. All right, we're ready. So let's open up the constraints file. And let's see what I have in my reference design. First thing I have is the GTH pins. Gigabit transceiver. So what are the proper names of all these things? I don't know. Let's open the design wrapper. Let's put it side by side. Ref clock. Okay, we want ref clock P. RX port. This is the RXP. And we want the TX. We want TXP because I believe that's the positive end. Next, I see SFP pins. So let me bring this stuff in. What's that? Dangling. All right, let's see. SFP TX disable. That name looks okay. Let's double check it. Yep. All right, so now we got the LED tri-mode. Oh, I forgot to do the, it's O, O, O. Okay, no, this is fine. So this is the LED. And we got the IIC, SCL, and we got SDA. All right, let's So now there are some timing constraints that I don't really understand, but we will just bring them in. So we have the IIC SCL, and we got the SDA, set false path. What does that mean? They're removing everything? And let's get the LED trim. Okay, so now this is everything. I should be able to generate Bitstream and we can get this going. All right, let's take a look at the design again. All right, let's save everything. Now I'm just going to go down here. I'm going to click Generate Bitstream. Everything completed. It didn't complete 2:40 p.m. That's the current time, maybe 10 minutes before. But anyway, we don't have to open the implemented design. We just have to do File, Export, Hardware, include Bitstream. And then I always put it in the root directory of the project. Finish. All right, so the XSA file will probably appear here. There it is. So what I like to do now, I'm going to create an SDK directory. I know it's been renamed to Vitis, but I'm just so used to working off of a directory named SDK. So I'm going to copy this path, put it into my clipboard. I'm going to launch Vitis 2024.1 Classic. I have it already configured to start up in Classic mode. So if you have Vitis 2024.1, it may try to go in the new extensible, whatever it's called. I'm not too familiar with it, so I can't really make videos about it yet, but this workflow will work with the existing. So it's going to ask me when it starts up to pick a workspace. I just created that directory. This is the reference project. I did everything in this directory, so I can look at something while I talk to you guys. So let's see. All right, POC KR260, POC KR260, SDK, select folder, launch. All right. Let's wait a little bit for everything to finish loading. All right, so first thing we do, we make a platform project. I name it Plat, you can name it whatever you like. Next. Now I'm going to browse. I don't like how Vitis starts off in this directory. Let's see if it's still on my clipboard. It is. So I'm going to click Open. I'm going to go ... into the thing, and there's the XSA file. All right. I mean, I'm not really going to change anything here. We're using the first processor, 64-bit. Finish. All right, so now let's say you want to make a change to these things. So we have first stage bootloader, then we have the bare metal application we're going to run. This is for a different processor. I think it's, well, it says PMU for Platform Management Unit, but I'm not exactly sure what happens. Anyway, sometimes maybe working on something and you want to configure the board support package. So you go Modify BSP Settings, and you can go, where is it here? You see, standard input, standard output goes to UART1. Remember how we added that to the design? Let's see. Okay, over here, extra compiler flags. sometimes you want to turn on more debugging. Let's see if I can get it. Basically, you add GCC compiler options to show more symbols. So sometimes you want to go in here and you want to I have it written down somewhere, but I always forget these tags. Anyway, not important for now. Let me shrink this so you can see it. So the board support package will not be built with debug symbols. Actually, I just remembered it now. So you go to the extra compiler flags and you would want to add -D to say define symbol, and then the symbol would be debug. So you would add that, and then the board support package will be compiled with debug symbols on. So that way you can actually see the source code of like the drivers you're using. So now I'm going to build this and it's going to take some time. It takes some time to compile, as you can see. That's only the first time. All right, it's done. So here's something I like. Well, lately I've been using C++. So we could just click next. We pick the platform. It should automatically be selected. Click next. And let's call this Hello World CPP. All the default options are fine. So empty application C++. So now what I'm going to do is that every source file that I add, I'm going to make sure I have it in source control. So I'm going to go outside of this directory, which is generated by Vivado. And I'm going to say new folder. Let's call it my CPP source. Now, if you look at this project, there's no source. I already have some IP that I want to bring in, well, some source code. So I'm going to copy it in right now. I have a file called main.cpp. And here's the cool thing. I'm going to go here. Let's see, add import. Let's see, import sources, browse. My source CPP. I'm going to copy the main. Let's see, is it going to copy it? I don't want to copy it, but if I have to, I guess I'll create links. I don't know if the links will work. Oh, don't want to do that. All right, let's just import it, see what happens. All right, so look at all these compiler errors. FIFO reader, DMA reader, I haven't brought it in yet. We're going to use just the DMA reader. We're not going to do FIFO because I haven't configured any of that here yet. So we're going to comment that out. Save. Let's build. All right, I can't find platform.h. It's because there is no platform.h. That's in my other project. We don't really need it. Let's see what's in platform config. Don't really need it. It's okay. Build. DMA reader. Yeah, I didn't bring that in. Okay, let's bring in DMA reader. Because we do have DMA, but I did not add any FIFOs that are without a DMA controller. So we can wipe this function out, don't need it. Oops, let's uncomment this line. All right, everything's looking good. All right, let's clear this. The OCD, it's a build project. Oh, didn't add this IP. All right, let's add some more sources. Import. Let's go browse. My CPP source. So I told it to import from this directory. Let's go to the directory of the SDK source project. Let's see if it copied the files in. I'm not too excited about that, but I'll live with it for now. All right, let's build. Of course, cleanup platform is not. Comment cleanup platform out, and let's build again. All right. Looks like we got a build here. So the first thing we're going to do is hello world, meaning we're just going to write hello world to the console. We're not going to sit here opening up, DMA panels and all that stuff. Hold on. Okay, so we said we're going to make just a hello world application that prints a counter to the console continuously. So let's take this. No, I thought I had the logic somewhere. All right, we're going to start by making a brand new one. So we're going to say int counter. We already got it. So we're going to say while true. Actually, let's see. Does C++ support the word to? Yes, it does. Look at that. We're going to sleep for 1 second, and we're going to print the standard out counter. So this program will not exit this because it's an infinite loop, obviously. All right. So now what we're going to do is we're going to turn on the KR260. One thing I don't like about the KR260, I think it's unplugged. Oh, it's back, is that it makes a lot of noise with the fan. So we turned it on, right? Let's just right click and say debug. This should work, even though I'm not going to do the boot with JTAG mode. It says that it configures it for you, but I find that it's not that reliable. All right. Let's go to the serial terminal. There's only one COM port, default settings for everything. All right, let's click F8. Look at that, counter, it's running.